Alright, so I have started my live stream to YouTube and also the live stream to Discord. So you guys should be able to see my screen, which is the Canvas site of CISP310. And all the text should be on the date specific channel. Yes, I did get Nitro, but I haven't used it on any of the servers yet. Oh, it does. Hmm. I did. I don't think I applied it to this server, but I might have accidentally done it. But I think Discord also has been revised quite a bit over the break. All right. So if anyone has any questions, yeah, we got another about 3 minutes before we actually start the lecture today. And it's pretty much like any other lecture, like face to face. If you have a question to ask, just go ahead and ask the question, and I will stop periodically to ask to see if anyone has any questions. So that would be a good time to ask as well. And I also keep an eye on the text channel of Discord. Although sometimes, because I'm focusing on the teaching material, so I may not see the text traffic as much. All right.
Professor?
Yeah, go ahead.
So I was able to get into the lecture, but I'm still on the wait list for lab. What should we do for that?
So there's not much to do until I take a roll today, so
Mhm.
that I can see how many people are not here today who are on the roster, and then I will start to let people into the class. So I'll start to send permission numbers according to the ordering, and it gets a little bit complicated because um, we have two wait lists, one for one lab and one for the other lab. And for all practical purposes, it really doesn't matter which waitlist people are on because we don't have a physical lab classroom. So I'm just going to lump both labs into one single one. But for enrollment purposes, there are still two separate waitlists. So I'll decide choose what to do with that. Um,
Awesome. Thank you.
sure. And there's a question about what happened to. Oh, okay. Wondering what LMS. LMS is the abbreviation of Learning Management System. So it's really just an abbreviation that we use in education. And Moodle, Moodle, is an open sourced LMS. Okay, I have been hosting my own Moodle server for many years, until the district decides to use Canvas. And when we switched over to use Canvas, one of the agreement with the OEI, the Online Education Initiative grant program, was that Moodle had to be shut down. So Litmus, what? Not sure what those two terms are. How LMS is. Oh, no. LMS does not stand for Litmus. It's Learning Management System. All right. Oh, so we exceed the 50 people already, I guess. So go ahead and use the YouTube channel. If you cannot get onto Discord and watch the live stream, use the YouTube channel. It should be at the very beginning of the text channel today. Does the Nitro boost increase the number of people? I thought the hard limit is 50. Okay, well, we can give it a try. So let me see if I can apply my Nitro on this server now. Alright, so server boost status. No server boost. All right, so I am plus 50 emoji slots. I don't need that. That's level 1 perk. Mm, it allows me to stream in high quality. Huh? Go ahead.
So server boost status.
Mm-hmm. Yeah, I know.
I believe that's a replay of your YouTube stream.
Oh, okay. So I'm looking for a clue where I can increase the number of people watching the live stream, and I cannot find any level that can do that. So even level 3 perks does not include an increase of people watching the live stream. It changes the resolution. That's one of the features, but it doesn't increase the number of people. So if you cannot get onto, so once again, if you cannot get onto the Discord live stream, use YouTube. Alright, so I got a few people typing, and I just want to make sure. Yeah, I think it is a hard limit of 50, regardless of boost level. Yeah. Alright, well, that kind of tells you the size of this class. We got 72 students on paper, plus 10 more on waitlist, at least. So that's a lot of people. And if there's a consensus, I can switch to Zoom as well. I don't really like Zoom all that much, but potentially we can switch to Zoom if the lag time of YouTube is an issue. All right, so can I assume everybody is watching either on Discord or through YouTube?
Yes.
Okay, excellent. All right, so I just want to keep my eye on the chat channel for a little bit longer. All right, excellent. All right, so I sent out a pre-recorded video on the syllabus. So this is the syllabus. You can read the entire syllabus over here. Twitch, maybe. Um, so I'm not going to spend any class time to talk about the syllabus unless somebody has a direct questions related to the syllabus. You can post it in the text channel, and I'll try to keep an eye on the text channel because it's scrolling up kind of fast. So I need to kind of scan it to make sure that I'm not missing anything important. All right. And I got two people, who direct text me. All right. So one, okay, got that one, and then the other one is from Isaac. So I think Isaac needs to go to the YouTube one. Okay. All right, there we go. All right, so I'm back to the server. And please do not use the general channel anymore because I can focus on just one single channel during the lecture. All right. All right. So let's try to keep the text channel on topic. You guys can use another channel, to kind of chat, but since I have to keep an eye on potential questions, related to the class, so I want the text channel to be on topic. Yes, so you can, if you see the word Moodle in the syllabus, you can replace that with Canvas. It's really just whatever the learning management system is. So we are not using Moodle anymore. All right. Excellent. Okay, so I think we are ready to get started with the actual topic. But before we do that, okay, I know, I said that I would start with the class topic. But before we do that, I would say CISP310 is one of those divide class. Okay, in most majors, there's a class that is seen as a divide class. Because it really tests whether someone has a natural talent, to pursue in that direction or not. In mathematics, I think it's abstract algebra. So I'm not trying to discourage anyone to pursue computer science, But I really think that a personality test can be very helpful to kind of understand your own strengths and to also assess whether computer science is the best major or not. Um, so I'm not trying to discourage anyone, but I think a self-assessment can be very helpful. So I'm just gonna throw this out, okay? You can totally just kind of toss it away and go like, this is bullshit, and I don't want to deal with it. That's perfectly okay, okay? So this is one of the websites where you can go for a free personality test, or you can pay for one that is more in depth. Okay, and they have different types of personality tests as well. So they have the Myers-Briggs, which is used a lot in industry. They also have Enneagram, and I think they have mixtures. Okay, so their Myers-Briggs test is not the typical one. It subdivides, under each letter, it subdivides into like 6 different facets. And so it's kind of interesting because at the end of the report, it would also have like occupation or career suggestions. So it is a pretty useful tool. Okay, I would say it's a pretty useful tool, and as long as people answer those questions, honestly, because some people answer the questions based on who they want to be as opposed to who they are, and that is not going to be very helpful. But as long as people are honest with the answers, the results of the test can be helpful. So I just wanted to toss this out, just to get it over with. And then we are now back to the actual topic that we will basically be talking about in this class. So you can see all of these links here, everything that has a little chain, symbol. Those are all material, reading material for this class. They're all here already. I don't have any time release, so everybody can just you can read ahead of time, way ahead of time, or you can just kind of follow along with the lecture. But my recommendation, other than the first class, obviously, is to read ahead of me by, I would say about a module or maybe half a module, because I'm just gonna get into these topics in this particular order. So you already know what I will be talking about based on where we are in a particular class. So my recommendation is try to read ahead of me by at least half a module. If you don't fully understand, the content of the module, don't worry. Write down your questions and make sure that I address all of those questions when I do get to that portion. But the idea is you want to prime your mind with the concepts prior to a lecture. That helps you absorb the material and also ask questions. Um, no, the module segments are not correlated to weeks. They are basically just an ordering, because you can see how some of these are longer and some of these are shorter. Some may look short but takes a long time to go over. So if you want to get a sense of when we can get to which topic, you can go to YouTube. Let me show you how you can get to the recorded lectures. So you can go to YouTube and look for my channel. So my channel is Some Profs. So once you get there, you can go to videos and you can search, okay, or you can just kind of look into this in a chronological order. If you find a day is missing, sometimes I forget to make the video public and they might be unlisted. Okay, so if they're unlisted, you cannot see it. If that is the case, if there's a day, you look up the calendar and say that day you're supposed to have a lecture, just let me know. I'll dig it up and then I will make it public. But that will give you an idea of when we usually get to which topic in the semester. Okay, so some people like to have that predictability, or stable, kind of stability. That's it. That's the word. Some people like to know when we'll get to what topic. So past semesters would be a kind of really kind of good clue to kind of show you by what time we'll get to which topic. So I hope that addresses the question of how long we stay on a particular topic. All right. So we'll get started with the first one, which is physical states, truth, numbers, and computers. All right, so each one is basically just an HTML file. I used to have PDFs, and then later on I just decided not to use PDFs because it is actually kind of difficult to make PDFs fully accessible and not be indicated as having a problem. All right, so we'll start with this one. And at any time, if you have a question, go ahead and ask the questions in the text channel. We'll start with physical states, okay? And I know there are a lot of words here, okay? So I don't worry about reading these things during the lecture, but you might want to read some of this before the lecture, okay? So physical states are physical devices are very it's kind of obvious, okay? Anything that exists in the physical world, as a device is a physical device. So we will first talk about, physical devices, electromechanical devices that have been used at least in the past to make computers. Um, so I don't know how many of you have watched the movie An Imitation Game. In that movie, Alan Turing, which is an actual historical figure, was using electromechanical devices to make computers that can decipher German encrypted messages. So those computers in that movie, they are electromechanical devices. What they use are rotors. They have rotors. Basically, it's a motor driving a rotor, and then the rotor has different electrical connections, and then there are static contact points. So by rotating the rotor, it can change the interconnection configuration between the contact points. Okay, so that's mostly the devices used in the computer in that particular movie, which is actually historically correct as well. In today's world, okay, we have electromechanical devices called relays. If you don't know what a relay is, you can just look up, electrical device relay. And a relay is a pretty simple device. What it is inside there's an electromagnet. There's a contact. There are two contact points. Usually, there are two, but sometimes there's only one. And then it has a reed. So the reed is attracted by magnetism, but normally it's spring loaded. So normally it is not contacting the contact point. But when the electromagnet is energized, it would attract the reed to go to the other side, and then a electro contact is made to close a circuit. So you can look it up, on Wikipedia to find out exactly how it works. But the bottom line is, it really is just a switch. Okay, it is a switch, but unlike a wall switch that you use at home, this kind of switch is special, because a wall switch at home, how do you actuate a wall switch? Well, you use a finger, right? You use something to bump it up or down to turn on or turn off something. But with an electromechanical device, how you turn on or how you close a circuit is by electricity. In other words, the mechanism or the physical quantity being used to configure or to control the device is the same kind of physical quantity that is being switched. Okay, so that is a very key component of devices that we use to make up computers. Okay, so we got electromechanical devices. They are very clunky, they're very slow, and they also consume a lot of electricity. But back at the end of World War II, those are the most commonly available devices to implement computers. So that's why they are used, in that time to make computers. And then people discovered or invented vacuum tubes. So vacuum tubes are also very interesting for those of you who like to understand physics and how things work. You can click on this link, which will bring you to a Wikipedia page that kind of talks about how vacuum tubes work. And there's one particular configuration of vacuum tubes called a triode. Okay, so if you click on this link, it'll bring you to another Wikipedia page that talks specifically about how a triode works. So what a triode is it really is a switch. Okay, it's just like a relay where the physical quantity that you use to control the device is the same physical quantity that is being controlled. Okay, and in both cases we are talking about electricity. So from that perspective, even though the physics behind the devices is entirely different, because one is mechanical and it makes use of magnetism to actuate the device and use a spring um, to specify the default state. The other one makes use of electrons on a heated surface in vacuum, can fly and go to another surface with a negative, with a different charge, with the opposite charge. So even though the physics is very different, they have the same abstract description. Okay, we are using electricity to switch electricity, to close a circuit or open a circuit, so that we control the flow of electricity using electricity. Okay, so both of these devices have exactly the same abstract mechanism. Okay, so we are not going to spend too much time here to talk about the actual detail of vacuum tubes. For those of you who are interested, I find it fascinating, how it works, but not everybody will find it interesting. But vacuum tubes also have an issue. Okay, they're not electromechanical devices, which means they are faster, but at the same time they still consume a lot of energy, because in order for vacuum tubes to work, it only works when the surface with a negative charge is at a high temperature. Okay, when I say high temperature, it will be the temperature of a glowing light bulb. So it's not like super hot, but it is still hot. Okay, you still have to use a lot of energy to heat up the surface in order for electrons to be able to escape from a surface to go to another surface with an opposite charge. So in other words, it's fast, but it's still consuming a lot of electricity, and it is still a relatively large device. Okay, because a vacuum tube is about the size of a small light bulb. Okay, because it actually has a small light bulb-ish thing inside. It's the filament that heats up the surface. So that's why it glows. Okay, because it has that heating element that gives off the heat. So we're gonna skip all the way now to transistors. Okay, so transistors, and the name of transistor is kind of interesting because we know what a resistor is, right? So a transistor is basically a configurable resistor. Okay, it can be, and basically it can be you can configure it so that it does not conduct electricity at all, or you can configure it so that it is mostly a conductor. Okay, nothing is a perfect conductor. Even superconductors are not 100%. Okay, there's always a little bit of resistance, a little bit of loss. Okay, so the actual mechanism of how a transistor is made is not important to us. Okay, because we are in computer science, we are not in electrical engineering. Well, most of us. Okay, because if you're in electrical engineering, you probably still have to take this class. However, most of us are not concerned about the actual physics behind transistors, but we are concerned about the behavior of a transistor. So more on that later in this module. Now, the nice thing about transistors, unlike vacuum tubes and electromechanical devices, is they are smaller. Okay, the first transistors were already quite a bit smaller compared to vacuum tubes and also electromechanical devices, and they're getting smaller and smaller and smaller and smaller, right? So from the 1950s, okay, they started to use transistors in computers in the 1950s. From the 1950s to today, 2021, we got about 70-ish years, right? So you might say, well, 70 years is a long time. Okay, but if you think about other devices, other inventions, let's talk about the jet engine, okay? Because jet engines started to exist at the end of World War II, okay? So in the same 70 years, jet engines have improved, okay? They have improved quite a bit, okay? So you might say, a jet engine today can be 3 times as powerful, okay? Maybe 5 times, maybe it's even 10 times as powerful as a jet engine at the end of World War II. And that's about all you can claim about jet engines. In computers, the original transistors were pretty big, okay? Even though they're small, they're still about the size of a coin, okay? We're talking about the size of a quarter, okay? And that's one single transistor. These days, if you look up AMD, they are using 7 nanometer process now, which means each transistor is quote unquote 7 by 7 nanometers. 1 nanometer is 1/1000th of a meter. So if you think about a coin, I would say that's about like 20 millimeter or so. So if you look at the ratio between 20 millimeters as opposed to 7 nanometers, that is a huge change, okay? We have shrunk transistors to a very, very small size, to the point where you can fit a lot of transistors across the cross section of a human hair, okay? That it really is just fascinating. And then the more you can shrink transistors, the smaller amount of energy it takes to change the state of a transistor, and as a result, the faster the transistor can change state, and therefore the faster the computer gets, okay? So Moore's law originally was only used to describe density of transistors, okay? How many transistors can we fit within a surface, okay? But it is also, okay, correlating to the speed of computers, because the smaller the transistor, the faster the computer can operate. And that's why Moore's law is very, very interesting, because it says every 18 months we will double transistor density, which roughly translates to every 18 months we're doubling the speed of computers. That is fascinating because it is exponential. Okay, we are not saying add 2. We are talking about times 2 every 18 months. Okay. So we'll go ahead and just continue with section 2.2. So with physical devices, we have physical states. Now all of the devices I have mentioned, they are all electrical devices. So the only physical state that we are really kind of interested in is voltage. Okay, well, voltage is the measuring unit. What it is measuring is called the electrical potential. Okay, that's it. So electrical potential is what a volt is. A volt is a measuring unit for electrical potential. Okay, and that is what we are interested in. Okay, because you can say if I put a voltmeter from ground, which is the 0 volt reference point, to a contact on the computer, what am I supposed to measure? Am I supposed to measure a low voltage, or am I supposed to measure a high voltage? So that is a physical state. Then we get to section 3, which is an interpretation of a physical state. Because if you just look at the physical property of a particular device, okay, it doesn't say anything about true or false. I mean, you can quantify a electrical potential at a certain point of a circuit and say, well, I'm measuring 0.25 volts over here, and I'm measuring 3.25 volts over there. That really is just the physical state, okay? But we assign interpretations to the physical state and say, well, let's go ahead and interpret everything below a certain voltage as 0, and we'll interpret everything above a certain voltage as a 1. So that is a interpretation. Okay, we are assigning meanings to physical states. And Aaron just posted an answer of 73,469 transistors will fit side by side in a penny. So that's just across, right? We are not even looking at the surface area. We are just lining up all the transistors on a line from one end of a penny, not even a quarter, to the other end of the coin. And I'm not sure. That doesn't sound right. I mean, it sounds like there should be it should be more. I could be wrong, but I thought it should be more. Give me a second here. I'm gonna do a quick calculation, which is also a time for you guys to think about what I've said and see if you have any questions. Okay, so let's do some calculation here. All right, so let's say a penny is 10 millimeter across, and then 1 millimeter has 1 million nanometers. So we got 1, 2, 3, 4, 5, 6, and that thing divided by 7 is, that's more, that's significantly more. Okay. All right. Well, if you want to know, you can always go to Google and ask, right? How many transistors across a human hair? Okay, obviously enough people have asked these questions.
Okay.
So in
All right.
yeah, go ahead. Okay.
Oh, wait, sorry. Could I ask a question?
Yeah, go ahead.
Okay, sorry. There was like a lag between the. I was watching the YouTube stream, so there's like a lag.
Mhm.
So if we're like randomly, or no, I shouldn't say randomly, but if we're assigning a truth value based on a voltage,
Mhm.
does that mean that execution on a CPU has some like level of uncertainty? Like, is it possible to like incorrectly read a voltage even when it is like true?
Well, that is an interesting question. So to answer that particular question, most most chips are based on an interpretation where a zero is registered. We register a contact point as a zero if the voltage is below a certain threshold, let's say 0.3, okay? And we register as a 1 when the voltage is above a certain point, let's say zero point 0.7. So now the question is, what about that stuff between a 0.3 and a 0.7, right? So depending on the kind of transistor we are talking about, that region in between is actually can be undetermined, can be considered undetermined in the sense that we don't even try to assign a meaning when the voltage is between the two thresholds.
Okay, I see. Thank you.
Okay. Oh, okay. I guess the lag is not too bad. Maybe a couple
Yeah,
of
no, I
seconds.
think I was just. Yeah, I think I was just focusing on your voice instead of like watching. So I was like, I was more in sync that time.
Okay, excellent. All right. So the bottom line is, there are a lot of transistors on a very small surface these days. Cool. Let me go back to the notes here. All right. And if you really kind of think about it, the whole idea of we're looking at something that is physical, but we are using interpretation to assign meaning to that stuff, that applies to just about everything, right? It applies to pixels on your screen, because if you look at every single pixel on your screen, it's just RGB, right? It's just RGB, 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 RGB. So how do you know? How can you see words and actually have meanings, coming out of these words? Well, that's because you're not looking at the pixels. You're assigning meanings to to special configurations of the pixels. That's kind of the difference between the physical state, which is really just levels of RGB, configured in a certain way, as opposed to, how should I look at that? What does that mean? Okay, because it is what it means that is going to be quote unquote processed. So we'll get back to this point, if not today, later on in the semester. We'll get back to this point quite a few times. Alright, so getting to section 3.3, we'll talk about a very specific kind of transistor. So this would be a good time to introduce the tool that we'll be using for this entire semester. So mastering this tool, understanding how to get it started, how to save files, how to navigate around it is going to be very helpful. Okay, this tool is called Logisim, so don't worry, your lab today has instructions. Okay, so don't worry if you cannot follow along what I do here, because there will be very detailed instructions later on during the lab time. But I will show you here, just so that this is recorded, and you might want to jot down the time too, because you can see that the time is down here. So right now is 6:01:18-ish. Just kind of jot it down and say Taki is starting to talk about how to get the tools set up at this time. So this way later on, if you need to, you can watch the YouTube video and just kind of move it to this particular spot. Then you can watch this part again, okay, without having to search for it.
But I will show you here, just so that this is.
Okay, I think I just heard myself. So what you do is you get to the shared folder at the top part of the Canvas site for this class, and I normally just open it in not a new window. Normally I would open it in a new tab like that, and that is new to me. Alright, there we go. Okay, so it still works. So once we get to the shared folder, we get to processor as a subfolder. So once again, you don't have to jot down the notes. The instruction will be given in the lab. And then over here, there are a few files that you need to download. One is alu.circ. One is regbank.circ. And then the other one is processor 0003.circ. So you have to download these files. There's one more thing that you have to download as well. So that is Logisim itself. And I have no idea where I put it. Yes, it will also work on the Mac because these are the tool is Java based. So as long as you know how to start up a Java program from a jar file, it should still work. And I would suspect that in Java it is very similar to how this will work in Linux too. So that should address the concern of people using Java. So you also need Logisim, and I think Logisim may be one folder up. Let me just look for that. Yep, there we go. So this is a jar file, JAR, as a basically it's a Java archive file. Okay, the J comes from Java, and then the AR comes from archive, which is basically just a zip file. It's a zip file with a whole bunch of bytecode files and some other stuff in it. So the idea is download the jar file, download the 3 files that I just mentioned, and depending on your operating system, you can start it in different ways. Okay, in Windows, I believe once you have JRE, the Java Runtime Environment installed, you can just double click on the jar file and it opens it and it runs the program automatically. If you're using Mac OS X or Linux, that may not happen. Okay, I'm not. I usually just use the command line tool to do this. So let me show you how I start this. Okay, so this is a command line tool, and I just have to say Java. Okay, which is the name of the JVM, Java virtual machine, and then you have to specify the jar file, the location of the jar file. Yes, it has not been sent to you. It is a link at the top of the Canvas site. So if you go all the way to the top of the Canvas site, under course information, if you click on shared folder, then you get to the top portion, the root of the shared folder. The Logisim file is in the shared folder itself, and then the circ files are in the subfolder called processor. You can just get to the share folder. There's not I can post it. ALU. It's in the lab, by the way. So ALU regbank.circ, and processor 0003.circ. But I know someone, some people like to follow along. There we go. And then we need Logisim 310.jar, but it's in a different folder. Okay, so the three circ files are in the processor subfolder, and then the jar file is not in a subfolder. All right. So my recommendation, unless you like to be super organized and you don't mind typing the full path to stuff, then you might want to put everything into the same folder. It just makes things easy to deal with. But I put things into different folders. Yeah, it would take a little bit of time for it to zip up. Plus, you will get a lot of files that you really can only utilize when you're on Google Drive, but that's okay. I mean, if you want to download everything at the same time, that's fine too. You still have to remember where to find that stuff though. Alright, so getting back to the command line here, so Java, and then you specify -jar. Basically, you're telling Java, the virtual machine, that it's supposed to run from a jar file. So Java -jar, and then you specify the full path. Okay, if you're running this command in the folder where you put logisim310.jar, then you don't need to supply the full path. Otherwise, you need to do the full path. Now, this only works in Linux and also Mac OS X. If you're using Windows, your slashes are the other way around, and then you have the, it's different in Windows. Okay. I can record another session for those people who want to do this in Windows and don't want to learn how to use the command line interface in Windows. Okay, which is a really useful skill to begin with. But I understand if people don't want to do that in this class. So I put my jar file all the way here. Okay. So that's how you specify the jar file. And then if you press the enter key, it should start Logisim the program. So there we go. So we got Logisim started up. Okay, my cats are fighting. Hey! Riley. I apologize for that distraction. And let me resize the window so it all fit in the recorded portion. There we go. Alright, so this is Logisim. What is WSL? I suppose I can Google search for that too. Windows subsystem for Linux. Nah, you don't really need that. I mean, you can learn how to do this command line in Windows. Okay, well, thank you. I didn't know the abbreviation before. So anyway, once you get here, okay, we can now play with transistors. Okay, so this part is kind of important. So you can see right here, this is where you can access different components that you can utilize to put into this area. In terms of programming, these things here are basically classes. You can use these classes to instantiate actual objects and then put it into this area here, which specify the actual circuit. There we go. In Windows, you can use terminal to do that too. You can use terminal on a Mac, yes. Yes, the jar file will work on both. So you don't have to start it up on from a command line interface. If you have Windows, I believe once you have Java runtime environment installed, you can just double click on the jar file and it will start there. No Java runtime present. So does that mean that there's no Java installed, then you have to install Java first. Alright. Okay, thank you. That's a good question. Which version of Java? I don't think it has a very it's not picky about that. Um, so my Java is an old one. I mean, this is like version 8. So I'm using a pretty old, ancient, archaic, Java runtime, and it still works. It's fine. On a Mac, I'm not sure. Okay, so on the Mac, you just have to install Java first. However, whatever you need to do to install Java first, that's what you need to do. Pretty sure, Java is available for Mac OS 10. So there's that. All right, so getting back to the circuit. So under wiring, we can see a few things. So I'll identify these things as we build the circuit. And you're going to have to do the same thing in your lab too. So the first thing is power, okay? And then we have ground. So these two are basically corresponding to the positive end of a battery and the negative end of the battery. So power is positive, ground is quote-unquote negative. And then we will start to draw some components here. So what we need are transistors. So when you click on the transistor, you can put a component over here. So let me just do this one more time. This is a single click, by the way. It's not a drag and drop. You click on a component to basically specify a class or type, and then you move the mouse, not drag, to the window area, to the main window area, and then you drop it. So when you drop it, you're instantiating a class into an object, and then the objects can be connected. Yeah, the application is really kind of old. It doesn't really handle high resolution screens very much. So one way to fix the problem is to decrease the resolution of your screen, so that it looks kind of normal. You can barely see the wiring. You can try to zoom. The zoom control is at the lower left corner. So anyway, let me just do this first, and then talk about the concept. Then we can talk about how to do it, using your tool or using your computer. So there are two types of transistors. So this is also an introduction to different parts of Logisim. This is your toolbox. Okay, this is how you can quote-unquote manufacture or produce parts to put into the actual circuitry. This part here is kind of like the members of a particular object, if I were to refer to programming concepts. So here we have a transistor. Once you click on a particular component in the circuit, it will give you a list of the properties. And the properties in this case include the type, phasing, gate location, and the data bits. So keep the data bits at 1 all the time. And then we can change the rest. Alright. So there are two types. One is called the P type, which is what this one looks like. Let me just duplicate this first so that we can contrast the two different types. So once you have one component selected, you can type Control D on the keyboard, which is a shortcut, to duplicate. So now we have two transistors. One is basically just a duplicate of the other one. So when I click on this one and when I click on this one, they show exactly the same properties. So I'm going to change one to an N type. So this is the one that I'm going to change. So you click on the drop down box and then you click on N type. So now we have one that is a P type, and then but we have another one which is an N type. So the only difference is whether there's a bubble here or not. Okay, so that bubble is the only indication that you get whether a transistor is a P type, which has a bubble, or an N type, which does not have a bubble. Okay, now this is a very important distinction. Okay, whether it's a p-type or not a p-type. So other than the bubble here, okay, there are 3 terminals. Now this is also important because, as you can see, when the mouse cursor is hovering over a terminal, it indicates that this is a connection point or connectable point. So that is really important, because if you draw a wire to anywhere else, there's actually no connection. Okay, you have to connect to the actual connection points, which are these 3 points over here. A transistor, whether it's n-type or not, has 3 connection points. This is the gate. So the gate is the easy one to identify because it is the one that is kind of, there's no symmetry to confuse about. Okay, this is the one that is sticking out from the middle. Okay, this is called the gate, which is where you specify the control voltage. Okay, and then you have the other 2 terminals over here. So these 2 are a little bit more confusing, because now it depends on the arrow. Okay, so the arrow is indicating which end is which end. Okay, so let me use some labeling here just for instruction purposes. Actually, I can do better. Let me show you my cool new tool. There we go. It's my remarkable. So remarkable is basically a tablet. It's a physical tablet, okay, and I can draw on it. So that makes it a kind of useful tool, because I can just kind of freehand draw. It's kind of like a electronic whiteboard, if you will. Okay. So, and because when I work on the tablet, I kind of have to use a different part of my desk, so you don't get to see me. Okay, and by the way, if anyone wants me to turn off my webcam, that's fine with me too. Okay, so if you want me to turn off the webcam, just let me know. So anyway, here's a transistor. So I'm drawing an n-type transistor because there's no bubble here. But whether there's an n-type or p-type, the terminology of the 3 connection points do not change. So now we have an arrow pointing this way. This is the gate, and the where the arrow is coming from, that is called the source. Okay, the source is over here, and then the drain is over here. Okay, so those are the 3 different parts or the 3 connection points of a transistor. Whether it's n-type or not doesn't really matter. So a p-type transistor would also have the same 3 parts, except there's a bubble for the gate, but it has the same arrow here, and the arrow is always going from source to drain. So now the question is, okay, so what is the big deal? Okay, so what is the actual difference between an n-type, which is this one, versus a p-type, which is this one over here? So what is the difference? Well, in a way, they're not different. In a way, they are exact opposites of each other. Okay, so the difference has to do with when is a transistor closing a circuit. So let me clarify what I mean by closing a circuit. When I say close a circuit, it means completing a circuit. It means turning on a circuit. Okay? When I say open a circuit, it is the same thing as saying disconnecting a circuit, which is also what we think of as turning off something. So connecting, closing, and turning on something really kind of mean the same thing. Disconnecting, opening, and turning off something mean pretty much the same thing. Okay, so those are the terms that we refer to when we talk about a transistor. So now getting back to the diagram. Okay, so a circuit turns on. Okay, so with both, okay, circuit is closed when, let me think about this. Okay, I need to think about this a little bit. When the source voltage is, I would say, opposite, okay, opposite to the gate voltage. There we go. So this description works for both N and P type transistors. Then you go like, okay, so what is the difference between the two types of transistors, right? They look almost exactly the same. They both have a gate, a source, and a drain. And they both turn on and turn off, using quote unquote the same principle. Okay, so you can also say that the circuit is open when source and gate have the same voltage. Okay, so that doesn't help, right? How do we differentiate between the two different types of transistors? So the next one is going to be the differentiator. Okay, for an N-type, source connects to a negative source. For P-type, the source, you probably can guess this already, connects to a positive source. That is the main difference. Okay, so if you compare the difference between the source and the drain with an N-type transistor, it's easy to remember because it's called an N-type transistor because the source is negative. For the P-type transistor, the source is positive. Okay, so that means in the diagram that we have, okay, I'm going to turn off the tablet, but don't worry, you don't have to copy everything down because it is being DVR'd by YouTube, so you can always refer to the recording if you need to. And the current time is 18:22, 6:22, almost 23. So just kind of write down that time mark, and you can always switch back to that one frame, and then you can just kind of copy and paste, cut and paste into your own notes. Okay. There's a question. Go ahead. Okay, I thought that was a question. All right. So now we look at these two. This is a P-type. Okay. Now how do we know it's a P-type again? Well, if you click on it, my mic is open. Oh, okay. Another person has the mic open. Alright, so let me check. There are actually a few people with the mic open, but only one person has background sound. Okay, thank you. Oh, the whiteboard, I have to turn it off. There we go. Okay. So getting back to the two transistors here, this is positive, right? This is negative. Power is positive, ground is negative. So the orientation of these two, this is a P-type, okay? So when I click on it, I know it's a P-type because the type says right here it's a P-type. So with a P-type, the source, which is where the arrow is coming from, is supposed to hook up to the higher voltage. So that means this end should attach to here. Okay. Yeah, sure. You can draw a picture like this. That's logically correct. Okay, but it's ugly. Okay, so let's try to improve this a little bit. Control Z would undo just like in the other app. So you can just Control Z and get rid of that line. So what we want to do is to rotate it. So rotation is not called rotation. It is controlled by phasing. Okay, so the phasing in this case is where the arrow is pointing. So the arrow is pointing from left to right, which is also known as pointing to the east. Okay, so we want it to point to south, right? Because we want the source to be pointing up, and then we want the drain to be pointing down. So now we control the heading and make it make the facing south like that. Okay, so that would be good. So we can move it around a little bit until we say, yeah, this looks about right. There we go. So we'll move the other one out of the way. And in the circuitry that we want to talk about, there are two p-type transistors. So we know, hey, we don't have to drag it from all the way from here again, because we can use Control D to duplicate. So Control D on the keyboard is a shortcut to duplicate a component, and it will duplicate all of the properties from the source thing. Okay, but this means this gate terminal is kind of pointing in the wrong direction, because we want it to be pointing to the other side. That is controlled by gate location, so we just have to flip the gate location to the other side. Now we have the two P transistors pointing from top to bottom, so that we have the source closer to the power point, and then we have the drain away from the power point. Okay. And the next thing we need to do is to specify the AND transistor. Okay, where is it supposed to go, and how do we make it look nicer? This is an N-type transistor because it doesn't have a bubble. Also, if we click on it, it will state that the type is an N-type. So this is how we can tell it is an N-type transistor. So with an N-type transistor, we want the source, which is where the arrow is coming from, to be connected to a lower voltage, to a negative voltage, which is the ground. So the ground is the most negative point in the circuitry that we are going to talk about here. So we want to rotate this, but this time we want to rotate it so that the facing is north, because we want this point to be closer to the ground, and we want this point to be away from the ground. So we want this to point north, or face north, like that. And then we can move it around a little bit so that it looks nicer like this. And we'll need another one of these too. So we'll make another one, and we can flip the gate location to the other side if we want to, just like that. Okay, so now we got all the well, almost all, not all yet. Okay, but we got almost all of the components here. What we are missing, so if you think about the circuitry as a function, we have now specified the body of the function. Well, most of it. Okay, we have specified most of the logic inside the body of a function, but we haven't specified the parameters. In other words, how does the outside world interact with this circuit? What is the interface between this circuitry and whatever is outside of this circuitry? That would be the job of the pins. Okay, so these two are the pins, and you can also use this pin tool over here. But my recommendation is use these two instead of the one over here, because the default setting of the one over here is not entirely right, so it's kind of cumbersome that you have to go back and change things. This one is an input pin, this is an output pin. So we'll need two input pins. Okay, so here's one, and here's the other one. I just have to kind of find a good place to put the other one. I suppose this is as good as a location as any. And we have an output pin, so we'll put the output pin all the way over here. So the input pins, as the name implies, are parameters. Okay, this allows the outside world to specify input into the circuitry that we are talking about. And then the output pin is collecting the result of this circuitry so that the outside world can get the result of this particular circuitry. So in a very rough sense, okay, the output pin is kind of like a return value, whereas the input pins are kind of like pass by value parameters. Okay, kind of roughly the same. So now we make connections. Okay, so you can see, okay, let me do this one more time. So when you make a connection, you gotta make sure that wherever you start, okay, is a legitimate connection point. When your mouse pointer is hovering over, it should light up a circle. Okay, and the same over here, because if you make a connection, let's say from here all the way to, oh, okay, I guess it won't let me do it, but you can do it the other way around. Okay, so you can draw a wire. Okay, now this is a drag action. you can actually stop a drag over here. So it would seem that you're making a connection, but it's not making a connection at all, because you need to make sure that the connector ends with a connection point, which is also known as a port. Okay, so got to be careful, because every year somebody would make a connection that looks like a connection when you visually look at it, but it really is not an actual connection in the circuit. So now we also want this wire, okay, to connect to over here. So you can pick any point to tap it, and then just drag a line all the way over here, and then drag the line all the way over here. You can see it automatically puts in a dot, okay, a really kind of thick dot in this case. The thick dot is indicating that these are all the same, what we call a net. Okay, so in circuit design, this is called a net, which is really just a fancy name of, it really is the same conductor on the circuit board. Okay, that's kind of just a fancy name for that. Now you also notice that I have been using, this is the selection tool. If you change to the poke tool, okay, this is called the poke tool, and you poke on a net, it will highlight the entire net. So this is a very useful tool to visually check to make sure that your circuitry is actually connecting the ports together. Okay, I see some people typing, or at least one person typing, so I'm keeping an eye on it, but I'm not stopping the lecture just yet. Alright, so but to continue to connect the components, you have to switch back to the selection tool. So we switch back to the selection tool, and we'll go ahead and complete this circuit, which is actually in your lab. Okay, I see a question popping up. The green eye of Soren. Are you talking about this one? So when people ask questions, please be specific. Yes, we do. Well, we have lab, today. Whether you want to do it at 7 o'clock or 8:30 is kind of up to you. Okay, so that's a very good question. What happens when they overlap? Okay, so I'll talk about that too. So the original question, that is the input, right? Okay, so these words are not helping. When people say this or that, I cannot see what you are referring to when you're using this or that. So let me show you a really cool tool that you can use. And this is something exactly, very good, Omer. Just take a portion of a screenshot and post it in the text channel. That is very good. Good job. Okay, that's exactly what I was about to say. Okay, this is one thing that you can do easily in Discord. Once you have a snipping tool, you can download one. Windows probably has one built into it. Then you can just copy and paste a portion of a screen into the text area and specify and say, this is what I'm talking about. So yes, that is an input pin. Okay, an input pin. Okay, how do we know it's an input pin, right? You click on it. So when you click on it, if it says no to output, it's an input pin. If you click on it and it says yes to output, then it's an output pin. So that's how we can differentiate an input pin from an output pin. Okay, so in Windows 10 you can use Snip and Sketch. Okay, I'm pretty sure there are third-party tools of all kinds to do this too. For me, okay, in Linux I have a shortcut key dedicated for snipping. So when I press the window key, the Windows key, and S at the same time, I programmed this, on my own computer. It brings up the snipping tool, and this is the pop-up that I see. Okay, let me move it into the window that you can see. So this is a screenshot tool, one of many. Okay, and I can now select a region. So I can now select like exactly what you guys have been asking about. Okay. And I also specify a 5-second delay because sometimes I have something that I need to do and I need to capture that moment. So now on the side it shows me this box. Okay, I have a few options. I can save it as a PNG file or whatever format I want to save it to. Copy to the clipboard, open with just a program so I can see it. So I can just click OK because I want to copy to the clipboard. Then I switch over to Discord and I just do a Control V to paste it, and there we have it. So on a Mac it's Command Shift 4. Okay, very good. And then in Windows is the window key Shift and then S. Okay, very cool. There we go. Oh, it doesn't work in WSL2. That's a Java thing. Oh, that's a X11 thing because the display variable is not set. There we go. Cool. So this is one of the many reasons why I like Discord, because you cannot do this in Zoom. Alright, so I'm just gonna finish the circuitry here. Okay, so I'm looking at the time. Yeah, we're doing good in time. Alright, so there we go. And then there we go. There. Alright, so now I really need to connect this point over here to this point over here. And you guys are smart and you'll say, but Tech, there's no need to overlap anything because you can do something like this. Just go around to the whole thing over here. So the answer is, yeah, I can do that, okay, to avoid any overlapping. But then I'm not illustrating what happens when we have an overlap, right? So instead of doing that, I am going to draw it right here and then make a connection from here to here. Then you go like, that is not good. I mean, because this is making a connection where it's not supposed to. So the reason why it's making a connection over there it's not supposed to. I wonder why it is assuming that I am connecting to that point. That is... Oh, I know why. I understand why, because this point here is actually a connection point. It's a port that belongs to the transistor here. So to illustrate what I want to illustrate, let me move the transistor down a little bit. So this point here is no longer a port of the transistor. Okay, so there we go. So when you just draw a wire like this and you do not stop and drop the wire on a particular junction, then it is assumed to be flying over. Alright, so let me explain what I mean by flying over as opposed to making a connection. This is an actual connection, which means this port, and this port, they're all actually connected. But this one here is a flyover because there's no big dot here like this one here to indicate that these two wires are physically connected. So this wire, the north-south wire, is actually not connected to the east-west wire. They are basically, one is over the other one, but they are not electrically connected. When you use the poke tool, you can also visualize and see that. Because when I poke on this wire, you can see this is it. This is the extent of the connection. It goes from this pin over here, this port of the input pin, to the gate of this particular transistor. But it doesn't light up or highlight the other wire. If I click on the other wire, you can see the 3 points that are being connected, but the wire that is flying over is not highlighted. So this is a really useful tool for you to double check to make sure that you are making the correct connections. I also want this to connect over here, and then I will take this one and then connect it over here. So now we have a circuitry done. The next thing we need to do is to analyze what is this circuit going to do. But before we can describe that, I will have to tell you what it means to specify a 1 here. A 0 is a low voltage, a 1 is a high voltage. So a 0 is the same at the same voltage level as ground, and a 1 is the same voltage level as power. Okay? So to specify a 0 means this point is now the same as ground, but if I change this from a 0 to a 1, that means this point will have the same voltage as the power connection itself. Are we still doing okay? Are there any questions? Okay, we got several questions coming. That's an output pin. Okay, that is a specific Mac specific question. I'm not sure I can answer that one. All right. You just draw the wires over. Don't stop in the middle and it will fly over. Oh, okay. So Logisim requires legacy Java's SE6 runtime. Okay. The transistor, you mean the ground? This one here, they're all coming from wiring over here. So once again, everything is being recorded. Okay, if you're not picking up the first time, you can watch the whole thing again and pick it up the second time. But the next question is good because when what I do on my mouse button is not visible. Hold and drag the wire, but just click for the components. Okay, let me just repeat one of the connections. So I'll go ahead and take out some of the connections, which is also a good demonstration because when you click on a wire, it will automatically select a segment of the wire, and you just press the delete key to delete that portion of a wire. And then you can delete this one too. So it's segment by segment. It does not automatically delete the entire net per se. So to make a connection, you just this is a drag action. Okay, so you press and hold the mouse button, left button, and then you keep going until you want to specify where that particular segment of the wire needs to go, and then you release the left button on the mouse like that, and then you draw the other segment like this, and then you draw the other segment like this. There we go. The lab is going to have instructions to show you how to download it, and I specified that a little bit earlier too. So don't worry, it is all in the lab instruction. Okay, so for the time being, just follow me. Okay, let me do the work first, and then when you get to the lab time, then you guys can get to do it. Okay, the instruction is there already. All right, because we want to focus on the concept first. Okay, in class, okay, we focus on the concept. In the lab, you get the hands-on to do it. Alright, so now the question is, okay, concept. When I switch, okay, you have to use the poke tool to change the state of an input pin. Now the state of the output pin you cannot change because that's the output pin is the return value. Yes, yes. If you have network connectivity problems, you can rewatch the YouTube recording anytime you want to. And the nice thing about YouTube is it's not a live stream, so basically if you have a slower connection, you would just basically have to re-spool, once in a while. Alright, but let me just click on this wire, make sure that you have using the poke tool. So when you use a poke tool to poke on an input pin, it changes the state of an input pin, just like that.
Anytime you want to. The nice thing about YouTube is it's not a live stream.
Okay, somebody has the mic turned on and using a speaker. All right. Thank you.
Just click on this wire, make sure that you have using the poke tool. When you use a poke tool to poke on an input pin, changes the state.
All right. So okay, I'm just gonna manually mute. Okay, there we go. All right. But okay, the important point here is the concept, okay? Because what I want to do is to figure out what the output pin is going to measure based on the input pins, the state of the input pins. Okay. So right now we have low voltage going to this particular gate. We have low voltage going to this particular gate. We have low voltage going to this particular gate, and also low voltage going to this particular gate. So what is that going to do to the transistors, right? How do we turn on the transistor? We want the source voltage to be opposite to the gate voltage. If one is high, we want the other one to be low. So when you look at this particular transistor, let me just click on it so that we can focus on just one. There we go. So when you look at the transistor that I have selected here, the source, which is where the arrow is coming from, is connected to the high voltage. But the gate is a low voltage. So that means this transistor is quote unquote on, or it is connecting the circuitry. This point of the transistor is now electrically connected to this point of the same transistor. So the same can be said about this transistor here, because it has a very symmetric configuration when both input pins are zeros. Oh, did I mute the entire server?
I don't think so.
The transistor is now electrically connected.
Yeah, because I just muted. Oh, okay then. Okay, so let me just mute it again. Okay, so I think I just muted one person and not the entire server.
Are you able to hear me?
Yes. Yes, I can. I think we're good. Yeah. Okay. Alright, so continuing on. So now the next question would be, what about this transistor here or this transistor here? So let's look at this one first. Okay, so focus on this particular transistor. So remember, when the source and the gate have the same voltage, it's off. When they have opposite voltages, it's on, right? The source is where the arrow is coming from, which in this case is this point here. It is coming from ground, which is a negative voltage. But when you look at the gate, it is also a negative voltage because 0 is negative voltage. So that means the gate and the source of this particular N transistor, they're both at a low voltage. And as a result, this transistor is off. It is disconnecting the circuit. And because it is disconnecting the circuit, and these two transistors are connected in series, so if one is off, the other one, can be on. It doesn't really matter. But this point is not even connected to ground anymore. And as a result, this point of the entire circuit is not connected to ground at all. As a result, if you start tracing from the output pin and back, this point here has a path to go all the way up to the power point. This point here also can go up to the power point, but there's no path to connect to the ground. And as a result, Okay, let me get back to the there we go. So I just manually unmuted, the one that was on earlier. Okay, so getting back to the example, um, this transistor is on, this transistor is also on. So there are two paths to connect the output pin to the high voltage. This transistor is off, okay, and even if this one were on, this one would have been off too, because this is a low voltage, and we know that the source of an N transistor is supposed to go to a low voltage, so this one would be off too. So there's no path to connect the output pin to ground. As a result, the output pin is now measuring a voltage of 1. Basically, we're interpreting the high voltage as as 1 or true. So are there any questions about this discussion? Because I think the concept is much more important compared to how do I run Logisim or install Java at this point, because the lab will give you plenty of time to figure that portion out. But right now it is the concept that is more important.
So, Professor, I had a quick question.
Yeah, go ahead.
When building transistors, it's essentially we're creating different combinations of voltage for to create a certain output voltage.
Well, the answer is correct, okay? But how many variations do we get out of this particular circuit? We already know that the input pins are Boolean. It can either be low or high, okay? This is high, this is low. Same with this one, right? This is low and this is high. But these two pins are independent, which means when this one is a 1, the other one can be a 0 or 1. And likewise, when the second one is a 1, the first one can be a 0 or 1. So there are 4 possible configurations. And we want to know, how the 4 configurations is going to influence the output, how each one of the 4 configurations is going to influence the output. That is kind of what the note is going to talk about too. So what I have done at this point is I'm just looking at the I'm looking for the web page here. There we go. Alright, so what I have done at this point is actually I have talked about everything all the way up to here. Okay, this circuitry may look different, but logically it is identical to the one that we are talking about. So now the question is, what is this circuitry actually doing? Why are we talking about this circuitry? That is the next question. And then we got some questions. If output has a connection to both ground and a power source, is the output 0? That is a very good question. The good thing is we are using a simulator and not an actual circuit. So the question is, if the output, which is this pin here, is connecting both to the high voltage, which is power, and is also connecting to the low voltage, which is ground, what is going to happen? Well, if the output pin is connecting to both of these points, then both of these points are connected to each other as well. That would be a short, okay? It's going to be a short circuit between power and ground. So what's going to happen then? I'm not sure. Now, don't do this. Don't try to do this. Don't try to trick someone else into doing this. But here's a question, okay? What happens when someone connects the positive end to the negative end of a car battery?
Get a nice fun surprise.
It's not just sparks, okay? The jumper, the cable itself, at least the insulator of the cable is going to melt. It's going to be hot, okay? And if depending on a lot of factors, okay, the worst thing that can happen would be the clamps would get welded onto the battery. So even if people want to disconnect it, 1 is going to be really hot, and then 2, is welded together, so they cannot be disconnected. So really bad things will happen. Okay, it's just a matter of, is the cable going to burn out first, or is the battery going to explode first? It's one or the other. Okay, so whenever you have a positive voltage source connected directly to the negative end of the negative end of power, bad things happen. Okay, you're looking at a lot of current passing through, and current passing through something that has resistance basically means a lot of heat. Okay, so bad things will happen. But in this case, it is not possible. Okay, so I'm going to challenge you. Okay, remind me to talk about this on Thursday. Okay, but I'm going to challenge you and say, well, how do we know that in this particular circuitry that there's no way for power to connect to ground? In other words, there's no way that at least one of these two is on and both of these are on at the same time. Okay, so you have to analyze the circuit and also analyze the possibility of the input pins and tell me why that situation cannot happen. Okay. Alright, so the lecture is done. Okay, in other words, we are actually 6 minutes over the lecture. So what I'll do next, I'm going to show you here. The first thing is I am going to take roll, but I'm going to take roll in a kind of convenient way, convenient for you and convenient for me. So the way I'm taking roll is I am going to open up the first lab, which is Logisim setup. It's a really simple lab. You just have to install, copy a few files, and stuff like that. But I will make the due date by 10 p.m. today. So there are a few things that you have to pay attention. Every time I open up a lab, there are a few things you want to kind of confirm with me. The first one is, can we take multiple attempts? Most of the time, yes, okay? But occasionally there are one or two where you can only take one attempt. So when you can take multiple attempts, I usually would use the highest score as the actual score, which means, if you don't get it right the first time, just do it again. Keep doing it until you get the highest score, and then you're good, okay? And there's no limit here either. So before the due date, you can reattempt as many times as you want to. Students see there's quiz responses. Yes, but you don't get to see the answer until the lab is past due. Then you can actually go back in and see the correct answer. Now for this one, I don't think it's going to be an issue. We're showing one question at a time, but this is the important part, okay? Each lab has, most labs, I shouldn't say each one, but most labs has an access code. So you want to know what the access code is for the lab. And in this case, it's just Logisim, all lowercase Logisim, Logisim. So you might want to jot it down and know that the access code is Logisim. And then we move on and talk about the due date. So I'm just going to use tonight at 10 p.m. as the due date. The date is 1 January 19th, and it's 10 p.m. And the availability is the same. Okay, so you can start on this as soon as I click Save and Publish. Okay, so I'm going to click Save and Publish here. So right now, on your side, you should see lab:Logisim setup, and you should be able to click on it. And once you click on it, it will ask you for a passcode. And once again, the passcode is Logisim itself, which is Logisim, or lowercase. So if you are having a problem getting into the lab, let me know. So what I'll do tonight for basically roll taking is to see who got into the lab and get it done. Okay, people who do not get the lab done tonight, will be counted as absent. So I'm going to type in the text channel. Okay, so the passcode of the lab is logisim. There we go. So I want to confirm to make sure that people can get into the lab at this point. Pretty sure that's the case, but I just want to double check. So if you're having issues getting in, okay, thank you. Thank you, Keaton and Nicholas. Okay, so for those people who are having problems getting into the lab, let me know, through Discord, and I will try my best to help you. And I don't think I need to continue the live screen sharing at this point, because I think this lab is fairly straightforward. I'll just double check and make sure. All right. Yeah, so it does have a few questions, and don't try to rush through the questions, okay? Because it's not really just a lab. The so-called questions, actually contain a lot of instructions. So you might want to go through this, slowly, and make sure that you learn everything that you need to learn from the lab itself. And if you want to do a screenshot, for each question, so that you have a backup, of these questions and the instructions, that's fine too. Okay, it's not a problem. Okay, so if you want to, go to each question and then take a screenshot or just print it out, so that you have a copy of each question, because the questions themselves also contain instructions. All right. So we got one person getting through the password prompt. Okay, so we are all good. Cool. All right, so it doesn't look like I need to keep the live session up. I'm gonna stop screen sharing, but I will still be on Discord. Okay, so I will be reading the text channel for today. So if you have a question or concern, just post it on the text channel. Or if you do not want the rest of the class know what you're asking, just direct message me. Okay, does everybody know how to direct message me? Does anyone not know how to direct message me and want to know how to do that? Just right click on my name and then select. Oh, okay, I need to click on somebody else. If I click on myself, it doesn't let me talk to myself, right? So right click on my name and then click on message. That will direct message me if you don't want the rest of the class to know what you're asking. Okay, that's fine. Cool. All right. Okay, somebody cannot get in. The submit is grayed out. Okay, I'll check on that. But let me disconnect, terminate the voice channel first. So disconnect the voice channel is just to click on that handset with an X on it. If you click that, you will disconnect. Okay, I'm gonna click it now, so I'm disconnecting now. There we go. And I will also stop